His is the first one.
Oh.
Yeah.
Oh.
Yeah. Okay.
When I say next slide, you are like, okay, I have this as well. Okay, cool. I'll just check if it works. Okay, it doesn't work. Yeah.
Down. What I forget? What I said?
At least one down? That's
Yeah.
pretty-
Yeah. Exactly.
Okay, okay. Kind of weird holding this, but all right. All right. Hello, everybody. I hope us all are having a great evening. My name is Akil, and I'll be your first presenter today. The topic of my presentation is a method of interpreting deep neural networks through gradient visualization. And I know that may sound complicated and verbose, especially considering that SCAI has not covered neural networks yet, but I promise to go over it to the best of my ability and simplify also to the best of my ability. This algorithm, I should give credit, was originally developed by Selvaraju et al. 2016, and this presentation will be an explanation and demonstration of their work, as well as explaining its importance overall. So for problem statement, while you may not know it, neural networks have been implemented in our everyday technologies, from self-driving cars developed by Tesla and Mercedes-Benz to our cameras, our iPhone cameras. Neural networks have been implemented in a lot of places in our lives that we may not know, such as even on Zoom, like blurring the background, things like that. So essentially, they have a lot of power. These are very powerful algorithms, and they've been implemented by a lot of big companies. Obviously, Microsoft, Google, Amazon, they all use these models, language models, things like that. And they're very powerful. However, one of the issues with neural networks is that there's a lack of interpretability. So what do I mean by there's a lack of interpretability? What I mean is that it's very difficult to understand why they make decisions. And for the user side, it may actually sound a bit weird hearing this. I know it was, especially for me, that a lot of these companies and people use these models and they can't actually explain fully what they do, which is why it's, in my opinion, very important. And that's what this presentation will try to do. So for example, in autonomous driving and computer vision, one of the really serious problems is that neural networks often misidentify people of color. So like people with darker skin, so like me, for example, will be misidentified, and obviously that could be terrible. For example, like imagine an autonomous vehicle misidentifies a person of color as like not a person, that would be terrible. So it's very important to understand this, especially when it's being used in so many areas of our lives. So before I go on to explain this method of interpretability, I'd like to explain a little bit of the architecture used, because this interpretability method is applied on top of a already previously trained network, which is a VGG16 network. This was trained by the Sony AI team, published on Nabla Labs, or that's the name of their Sony AI lab. And this network was pre-trained on ImageNet. ImageNet has over 14 million images, 1,000 classes. Obviously, I had to use this pre-trained network because I could not train one from scratch unless I had an RTX 4090. So the images I used for testing this were obtained from Flickr. I used a script created by Professor Jeff Eaton of the University of Washington in St. Louis to pull images from Flickr using an API. And these images are fish, which is how they're related to the project, because fish is beneath the depths, beneath the ocean. That was my interpretation of that. So here I go into some of the specifics about the VGG16. And I know it's a little bit kind of intimidating looking at this because it's very large and it doesn't really make that much sense when you first look at it, but I'll explain it. So essentially, this is something called a convolutional neural network. And what this does is it takes an image and it essentially prepares the image to be analyzed by a neural network. So a neural network cannot understand images on their own because images are multidimensional. They're obviously squares, as we can see there. And images, neural networks can only understand vectors. So we have to convert this image essentially into a vector. So how is this done? It's done through convolutional layers and pooling layers. The convolutional layer applies a filter and a dot product to the image, and that result is then pooled, which essentially just kind of obtains the smallest or the largest or average value of a certain part of an image, essentially. And all that really needs to be understood is that this process is applied multiple times to downsize the image so that the neural network can understand it. At the very end, before a neural network understands it, vector essentially summarizes summary of the image. That's how you can understand it, is that it understands certain parts of the image, such as the bushes, or maybe the ocean, and those features are essentially concatenated or summarized in just almost scalar values so that the computer can actually understand it. The main idea, essentially, like I explained earlier, kind of, that the convolutional neural network, specifically VGG16, essentially learns patterns in an image. For example, outlines, like the sky, things like this, any patterns that we see can also be learned by neural networks. So that's why convolutional neural networks is VGG16. So now we can move on to the main topic, and I know this looks kind of crazy, so I'll go over each part. So this is GradCam. GradCam is the interpretability method that was again developed by Solaraju et al. 2016 that I'll be analyzing. So at the top row, we see the standard procedure for a convolutional neural network that I described earlier. After the final convolutional layer, we have a vector that's passed into a deep neural network, which makes a class prediction based on multiple layers in the deep neural network. In this example, we have cat, dog, and fish that are predicted. The bottom row is a description of a simplified version of the GradCam procedure. Once an image has been classified by the neural network, we take the gradient of the class decision with respect to feature layers of the network. For instance, we could have our feature layers simply be the colors red, green, and blue. Most of the time, there's other complex features like I mentioned earlier, such as outlines, the sky, things like that. But this is just a very simple example. So after this, for each class, we sum the gradients with respect to each feature layer. We take the sum and we take an average, and this is represented as alpha. And after alpha has been computed for each feature or for each class label, we compute a linear combination of each alpha value by each different feature map. And when we take this linear combination, we receive a 16 by 16 heat map, which is then upsampled to a very high resolution that we can visualize. So essentially, I know that sounded a little bit complicated, but the most important thing to remember is that GradCam allows us to retrieve the most important parts of the classified image. So by going back in the network and essentially retrieving what activates the neural network, we are learning what parts of an image were the most important in that classification decision. So this is a really cool part, and this is why I said it's really nice. So here are the results, and here we have an image of a goldfish in coral. It appears to be in an aquarium because you see that kind of black box on top, and we see that the class label has its own color. So for coral reef, the color is represented by a lighter yellow that's kind of over here, and then the goldfish is represented by the darker color, essentially over there. And we see what parts in the image are highlighted for each classification decision. So for the coral reef classification decision, the kind of outside area, this area was highlighted by activating the network when it made the decision. And with respect to the goldfish, the center, well, the goldfish, I guess, in the middle of the image was highlighted as activating the neural network. And we can see the difference between the coral reef and goldfish. In the goldfish classification, the coral reef didn't matter too much. So that is quite interesting. I also have another example. In this example, we have what appears to be a lionfish. swimming in an aquarium. And with respect to the lionfish classification decision, we see that the network correctly highlighted the center of the lionfish, as well as its tail and its fins on top. And what I found interesting was that, when we look at a lionfish, when you look at this fish right here, what's the first thing you notice? The first thing you notice is its spikes. It spikes on top and it spikes on the side. And when the neural network learned that image, was given that image, it also had the same thing. It activated the sides, top, and the center of the lionfish. That was what's most important for the neural network with that classification decision. And just for fun, I wanted to see what would happen when we take it with respect to goldfish. Obviously, when we look at this picture, we see that there's no goldfish here at all. There's just a lionfish and what appears to be another lionfish in the background, so probably no goldfish in this image. And with respect to the goldfish image, it highlighted some kind of weirder regions, like highlighted the fish in the background. And so it highlighted some kind of noise in the background essentially, because it struggled to make that classification decision. And for kind of a more interesting slide, for that previous image, the top prediction was lionfish. That was that is correct, that's a lionfish. But also it made some other quite weird predictions. Of course, we could always go back and look at the heat maps for each of these images. I don't want to do that because that'd take an hour. But we can see that lionfish, jellyfish, lobster, those are all sea creatures, and those are the ones that it believes are most prevalent in the image. And we have obviously some more weirder ones that may actually give more interest. We have garden spider, fountain, and tiger. Of course, we all know those class labels are definitely not in the previous image. So, but it would be interesting to see why the network believed that. So we can always go back and take a heat map with respect to those images. So there's actually some limitations of GradCam. So while doing research for this project, I discovered that it was kind of a big limitation. So two authors, Drelos and Carlin, in 2020, they published a paper where they kind of claimed that GradCam had some very serious errors. They stated that GradCam actually highlighted incorrect areas with respect to the class label, and they proposed a alternative called high-res cam. And maybe a little bit more specifically, their proposal, rather than taking a summed average for each class label with respect to feature map, they directly multiply the feature map by the gradient of the class label with respect to feature map. And well, specifics, but we can see in this example the difference between GradCam and high-res cam. It seems that high-res cam is slightly more specific, whereas GradCam just kind of is a little bit more blurry, and it does highlight the main parts of the image, but it's certainly not as accurate as high-res cam. Of course, high-res cam is in 2020, GradCam is in 2016. So as time goes on, of course, we're going to have better interpretable, and more accurate models. Anyway, that was my conclusion. The project was very interesting to me, and I think it's important to analyze why these networks make these decisions. So thank you for your attention, and my time for questions right now. Exactly fully search that paper, but from what I remember, essentially it got rid of the part where it takes a weighted average and it just directly multiplied by the feature map rather than taking an average like for each feature map with respect to each label. So it kind of, yeah, it kind of took, it's like, this is kind of common in machine learning actually, where taking out the step will actually improve the performance. And it seems to some extent that's what they achieved. They achieved better performance using that. But their claims, to be honest, they never directly proved their claims. It didn't have the paper didn't seem to have that many citations, and it's a little bit. It was never published in any conference, so maybe a little bit of skepticism. But the results are accurate, so they could be right.
Any final questions? All right, very good, thank you.
Yep. Fish sizes. Awesome.
Like button in the middle.
Yep, okay. So this is my SCAI project. I just called it fish synthesis, but it is essentially a CNN trained for image classification on purely synthetic data from a fine-tuned diffusion model. So in this project, I'll go over the methodology for that, the results, and then some setbacks and improvements, and finally, the implications for this in image classification as a whole subset of AI. Let's get started with the introduction to the project. So when I thought about depth below, kind of like a keel, first thing I thought about was sea. So anything under the sea, submarines, fish, sharks, anything. And so I went to Google and I searched up, marine AI, marine data sets, and there were some interesting results in some cool projects. But more importantly than anything else, what I found was there isn't a lot of data. One of my original goals was to make a plastic detection model for marine environments. And so I read a paper on that subject, and it turns out there are no known data sets for that subject. So the research author for that paper actually grabbed a wetsuit and drove across the coast of California, and with his own little collection of plastic, dumping it into different rivers, taking pictures, picking it back up, of course, and then going back, annotating and cleaning his data set, and then finally he's able to get to what he actually wanted to do, which is develop an architecture for this task. So I decided I wanted to do fish classification, kind of like what Akil did, but instead of objects in general, it's just specifically fish. Given an image of a fish, output which species it is related, or which species it is. And I found this chiral data set on this exact task, this one here. And to my surprise, it actually had a lot of data. It had 9 species of fish and 1,000 images for each species, so 9,000 total. But I wanted to do this task, but I wanted to do something a little bit different, something novel. And so I decided to replicate the scarcity that exists in a lot of marine data. So what I ended up doing was I scaled down the project a little bit. Instead of 9 species of fish, let's do 3 species. And instead of 1,000 images for each species of fish, so that's 3,000 total, let's scale that down to 50. So 50 out of 1,000, or 5% of the original data. And if we can find a way to create a CNN, which is at a high enough level to be in a production environment, that would be incredible. That there could be large scale applications for this. And in today's project, I'll be going over how I managed to do something similar to that. So there's a few approaches to making an AI model better, and the most obvious is more data. Unfortunately, we don't have a lot of data here. We only have 50 out of 1,000 images. So there's a second approach, which is to generate the data ourselves using image synthesis. For those of you familiar with image generation in AI, the first thing you probably think about is scans, or general adversarial networks. And those work by taking 2 models, training one generator and one discriminator. The generator is basically trying to trick the discriminator into proving that whatever image it has is similar enough to fit the data set that the discriminator has been training on. That's just a high level overview, but generally speaking, for these projects, GANs are typically used. Now, the problem with GANs is that they actually take a lot of data and computation time. And with 50 images, the best result we're going to get with a GAN is just an outline of a fish. And that's not sufficient to train a CNN on. So we need something that gives high quality data and diverse enough such that our CNN can improve over time. So why don't we use a model that has been trained on 2.3 billion images called Stable Diffusion. So I'm sure most of you have heard of Stable Diffusion. It's probably the most popular deep learning model today. It's a diffusion model by Stability AI. It's open source. And down here are some results from there. Stable Diffusion has most commonly been known for its output of art. It's a text to image model. So you input some text and output an image. And, it comes up with some really cool results. They look really realistic. They look like a digital artist would have made them. But not much has been done to utilize this power for creating data, which is like the most valuable thing you can do with AI. So, unfortunately, I can't just ask Stable Diffusion to give me an image of a trout or give me an image of any species of fish. It's not going to fit the original data set at all. And it may not even know what a trout is, despite, being trained with so much data. So we need a way to fine tune this data set. So that's where I came up with the overall pipeline for this model, which is to find a way to fine tune Stable Diffusion, upload that to Hugging Face as a model pipeline, run some predictions, and that had to be deployed on Nautilus for the reason we'll get into. And then finally run some sort of experiment with a CNN on our purely synthetic data. So let's go into the first part, which is fine tuning. So as it turns out, fine tuning a diffusion model is rather complicated. There are two approaches to fine tuning a text to image diffusion model. And that is currently textual inversion, where we're trying to fine tune the original text such that we get an output that's similar enough to our original data. And there is Dreamboot, which is developed by a team of Google scientists. And I decided to go with Dreamboot because it makes more sense for fine-tuning the entire diffusion model. It promotes diversity in the data set, and the results are just plainly better. So this is just I just grabbed this image from their paper. I'm not going to go too into depth with all of it. It's a little bit complicated to describe in the scope of like a 15-minute presentation or 10-minute presentation. But what's important to note is you see here, there's a custom prompt. So these text image models take a prompt and output a image. So textual inversion, like I said, will fine tune that text, the text prompt, but let's find a way to use a constant prompt and then fine tune the actual image generation prompt. So Dreamboot works by creating a constant prompt with the word a and then a unique identifier. And by unique identifier, we mean anything that's not an English word. So for one of the images I was generating was trout. So I decided to come up with a fake name of fake trout. It's not an English word, so it would not pick up on that. And then finally, it will want a classifier to come up with a general noun for that. So for our example, it would be like a fake trout fish. Is probably what we come up with as a prompt. Then it works by fine-tuning the entire diffusion model. And there are a few issues here with language drift and overfitting, which are just, generally speaking, what that means is that the model is forgetting how to create the original images. Again, I can't get too into depth with it, but the way that Dreamboot solves this is by using a custom loss function, which is called an autogenous fire preservation class specific loss function, which again looks really complicated, but it's actually, generally speaking, pretty simple. What it's essentially doing is taking previous generations of what the diffusion model is outputting and then supervising the learning with those previous generations. So after working through that and implementing Dreamboot for Stable Diffusion, we can look at some preliminary results, which are pretty impressive. So here we have the real images. These are the 16 trout images I outputted, and these are 16 fake ones. I think it's pretty hard to tell the difference between which ones are real and which ones are fake. A little bit more up close, like I had my roommates choose which ones are real and which ones fake. They got it right, but it was pretty tough. And I think these results kind of show that. So you can see here, it's managing to pick up on the features of a trout, like the spottedness. Maybe it's a little hard to see from further back, but it looks relatively similar to the original data set. The lighting is all good. We have different angles for diversity. The results are pretty good. Now what we need to do is actually generate a data set. So it turns out to create results that good, or to use a model this big, it takes time. It takes around 30 seconds to generate a single image. So that translates to like 75 hours of training if we were to do 9,000 images. That's kind of why I scaled down the project to 3 species. And then also, I didn't want to generate 1,000 for each. I just ended up generating 300. This takes around 7.5 hours, but it's still pretty annoying to do on pull out because of memory exceeding errors. And then if I was away from the computer, it would disconnect. So thanks to Cohen, I was able to set it up on a Nautilus cluster where I could just have it run a more powerful GPU and I'd be away from the computer. And so after around 10 hours of training, I was able to generate a data set. And I had this data set uploaded to Kaggle. I can like link it if anyone's curious to look at it, but it is just 300 images of the 9 species of fish. Okay, so we've done pretty much everything in the pipeline. We've fine-tuned a stable diffusion model. We have generated the data set, and now we're ready to actually do training. So, Akil kind of explained what a CNN is pretty well. And this again is just a CNN. CNNs are pretty commonly used for image classification tools. This takes a 512 by 512 by 3 size image and then runs through a series of convolution layers and finally 2 fully connected layers. The convolution layer architecture was mostly inspired by other type of local playstyle, and then the fully connected layers were just customized because of some loss issues or overfitting issues. So I just increased the neurons and then added a dropout layer. And over here, this is a Keras summary, which goes into a little bit more depth with numbers in case anyone is curious. And so now we're ready to actually look at the results. But just fine tuning a CNN on the data that we came up with doesn't mean anything. We could get 67% accuracy and not know if that's good or bad. So we need some sort of way to compare this. So after a little bit of thinking, I came up with a relatively simple experiment to figure out how good our results are. So let's take one CNN, we'll call it the real CNN, and let's train it on our original data. So that's 50 per every 1,000, right? That's 50 by 3, 150 images. So it's training on 150 images on the same architecture on 10 epochs. And let's train another model, we'll call that synthetic CNN, which takes the original 150, adds the 900 we created, and let's train that on 10 epochs, same architecture. And another important thing to note is we don't want to check accuracy against the fake data. That doesn't mean anything for us. So the validation sets are made of purely real data from the original Kaggle data set. So without further ado, let's look at some results. So these are some screenshots of the best epoch from each of the 3 models. I'll get into the third one a little bit later. But the real CNN achieves a fairly respectable result of 80% accuracy and 82% validation accuracy. That's fairly impressive. It's definitely nowhere near production value, but it's okay. And on 150 images, that's respectable. With synthetic CNN, so again, we have no additional manual labor, and we generated 900 new images. We were able to achieve nearing 99% accuracy and 94% validation. So that's like a 15% roughly increase in validation accuracy. That means on real data, and then a 20% increase in actual accuracy, which I think is pretty impressive. And then we have the improved synthetic CNN. This is just including some best practices for CNN training, which means like reducing learning rates on plateau, some additional Keras callback features. We achieved 99% accuracy and 95% validation, which is absolutely respectable for any sort of production quality model. So without lifting an additional finger, without looking into any more data, we were able to increase the accuracy by 15%. There's no additional complexity in architecture. We didn't invent anything revolutionary. We simply just used what already exists but hasn't been explored yet with Stable Diffusion. These are some additional results on the improved CNN. So I decided to just plot the validation and training accuracy over epochs. And this is a confusion matrix, in case anyone was curious. These are 3 species of fish that, I guess, not really fish, but it's fine. The 3 different species that this is trained on. And so let's also acknowledge some like setbacks and improvements for the future. So the CNN didn't work well on all 9 species of fish. There were 2 species of fish specifically, the red mullet and the striped red mullet. And the striped red mullet is literally just a slightly whiter version of the red mullet. So it did not perform well. Like the synthetic data did not pick up on that incredibly well. The best way to fix this is just use more data, but that's kind of like contrary to the entire purpose of this. And the other idea is to use some sort of pre-trained GAN or highly complicated GAN, which would take a lot of computing time, but there may be an approach there. The other issue is the overfitting. And overfitting was caused by lack of diversity in training data. So I kind of countered that by increasing dropout percentage and adding additional dropout layer, an additional fully connected layer. But there's a second approach to this using Green Booth, because it turns out Green Booth is really good at creating data without any information. So what that means is, let's say I gave a photo of just the face of a corgi to Stable Diffusion, or I guess Green Booth, and I asked it to fine tune on this, and then I asked it in the prompt, give me a top-down view of this dog. It will actually understand that this is corgi and will give a very hyper-realistic result from the top-down angle. So we could use this to create different angles for our data set, and that increases the diversity. Now, the reason I didn't do this is because I wanted to show for this demonstration how much we could do without any additional manual labor. And so I decided not to deal with, adding different manual prompts, because what I wanted to show is, we're not putting anything else into this model. It's simply just all automated. So those are the improvements that can be done in the future. And yes, this last slide is just dealing with the implications. So, let's say you're part of a club on campus, a nature club, and for some reason you need to create a classifier model for your club, maybe classifying on slugs, right? Right now, your best bet is to go onto Google, find a data set of slugs, hope that your species specifically are there, hope that you have enough data, and create a CNN on that data set, that curated data set. The other option is to curate the data set yourself, which takes a lot of time and a lot of knowledge. But if we're able to use this pipeline that I just described, theoretically, we could just gather 20 to 50 images from Google Images, literally just rename the files, go through the fine-tuning process, train our CNN, and again, theoretically achieve results that are worthy of production capabilities, 95% validation reviews. Currently, this field is like incredibly unexplored, which is why I wanted to show just what happens when you search up Stable Diffusion and go to Google Images. All the results are art-related, and actually, in fact, when I started this project and I searched up Stable Diffusion image synthesis or data synthesis, there were literally only 2 results that were like worth looking at. And over time, there's been a few more papers that have been created. So this field is incredibly novel and or incredibly new, and has a lot of large-scale implications on any image classification task. Obviously, what I've shown today is the ideal case, right? Eliminate a lot of different species, use ones that are really different from each other. But I hope that today you've been able to see like what the results of image generation in AI can do, and maybe you want to look into this in the future as well. Thanks. That's pretty much it.
So I know you talked a bit about this at the beginning, but you decided to go with Stable Diffusion over GAN. What was that reason again?
Okay, so with GANs, if I gave it 150 images to train on, I found that the best results I was getting was just an overall highlight of the model or of the data. And theoretically, I could use more complicated GAN infrastructure, like a better model for generating and discriminating. But what would happen is that it would tend to there would be no diversity in the original data. It wouldn't pick up on the same amount. And the data would also be kind of noisy, which would lead to some finicky results with the CNN outputs. So, the only advantage of Stable Diffusion over the GAN is the fact that it's been trained on 2.3 billion pieces of data. So that kind of helps with all.
Have you check whether your synthetic results work better than like other things like Dolly? So David has a very similar process of putting in text and getting out
I tried Stable Diffusion because it's open source.
yeah.
Any other questions? Nope. All right. Oh, what?
Yeah, so for that classification accuracy is pretty good. But do you think that you might, like in a real world setting, like let's say like you're actually exploring the ocean, maybe like hundreds of years from now, do you think that, or just go in the ocean, do you think that you'd still have that same accuracy, or do you think that just because it was curated?
Yeah, absolutely not. There's like no way we would have that in a real life scenario. But the reason I chose this data set specifically was because it had a lot of data. So I wanted a validation set which I could actually validate my images on. There's not a lot of data sets for or I guess there may be, but I chose one which can specifically have a lot of validation data for my experiment. So this is for the purpose of an experiment, and the results are pretty good for that case.
Anything else?
No.
Nope. Awesome. Thank you. Next. Yeah. What's the time? 6:40. What's time am I?
How long would it,
Kevin.
how long would it go to take? Okay.
Okay.
perfect.
Hi, everyone. I'm Kevin Bachelor, and the SCAI project that I just do was on wave and tsunami analysis. So, down, right. Beginning with kind of the exploring the kind of theme and goal of the project. My partner and I, when I had a partner at the very beginning, we explored a bunch of possible options for the theme statement and really just looked for data sets for inspiration. We searched a bunch of places, including Kaggle and the UCI machine learning repository, and as well as just Googling for stuff. And our main goal was we wanted something with some kind of concrete use, some kind of way that the model could be used for, actual research in the future. And eventually, we stumbled upon this tsunami and wave data set from Kaggle. And what it was essentially it had a bunch of information about tsunamis and waves leading up to them. And it related them using tsunami IDs so we could actually have the correlations between the two. And we took this data and we cleaned it up a little bit so that we could analyze it best. And we took of the many different pieces, many different parts of the data. We took three specific things: the Soloviev ID of the tsunami, which is basically a way of measuring the tsunami intensity, the max height of the wave, and the inundation of the wave, which is how far inland the wave goes. And this brought the data set down from about 2,000 data points to 300. There was lots of graphing and analyzing different relationships to choose these specific values. Yeah. So the model we used was just a neural network. We wanted to write it from scratch at first, but then as school came along, different things, et cetera, we eventually turned to PyTorch. And we actually used a general model that was specifically designed with high reusability in mind in case in the future we wanted to do more stuff with it. Now we used one with 2 activation layers. It worked best with linear layers that turned input into 200 to just kind of use the activation layers. And then we also saved the file for, yeah. So accuracy. There's a reason this slide is right before the improvement slide. But basically the testing accuracy faltered around 40%, which is a little unfortunate. And here you can see it didn't do well with a lot of the higher Soloviev identification numbers because we didn't actually have that many data points with those. But for the lower ones, like 1 and 2 a little bit, it did a lot better. So possible improvements that we wanted to make was essentially aimed at making the model less inaccurate and more reliable, because as you saw earlier, 40% is not great. So we would possibly want to implement it with lots and lots more data. We had to narrow it down to 300 just because of how it matched up, and that really just, I feel like it wasn't enough, and a lot more would have done a lot better. And possibly even looking at different values rather than the maximum height and the wave inundation for what to use in each data point. We could also experiment with the model parameters more because we didn't have much time to do that as we submitted it close to the deadline. And possibly in the future, collecting our own data would be nice, as we could get a lot more specific data per wave, rather than having a bunch of them missing a bunch of the information and having to toss out significantly more than half of the data points. Thank you. Any questions? Yes.
So you mentioned you reduced the amount of data because of it not matching them. What does that mean exactly?
Sorry. So essentially, there was a lot of the different data points had different, all these different values associated with them, and then most of which were just null. And we only took ones that had wave ID, or not wave ID, sorry, that had the maximum height, the inundation, and the Soloviev ID, which wasn't a lot of them. And then also they had to have a certain ID relating the tsunamis to the waves themselves, because there were 2 different data sets that we combined, and there was a value that kind of connected the two, and some of them weren't connected. So it was just, a lot of it had to be scrapped.
I have a second question.
Oh, yeah.
So could you just briefly go over which, like, the input neurons, what parameters are there? If like you were missing a lot of data, was it just those three pieces of data?
Yeah, it was just those three.
Okay.
So you built your own neural network, not from scratch, but the individual pieces. How did you choose which pieces to add where at what size?
It was essentially just trial and error, unfortunately. If I had more time, I definitely would have researched that a little bit more. That's one of the things that I wanted to experiment with the model parameters and model architecture more, and actually do some research into what would make it the best, but it was essentially just trial and error. Right?
Any other questions? No? Oh, you look like you're on the fence.
So, okay, it's kind of, what exactly were you trying to predict?
Sorry, yeah, okay, so the Soloviev ID was actually the thing we were trying to predict. The parameters were the wave inundation and maximum height, and the Soloviev ID, which is kind of the size of the tsunami that said waves would create, was what we were trying to predict. So given a number of waves, we wanted to predict based on their height and how far inland they went, how big the tsunami followed.
All right,
Thank you.
Thank you.
any last one?
Hi, my name is Anshul. I use they, she pronouns. Alright. And my project was to predict the location of earthquakes, specifically latitude, based using depth, magnitude, and some other factors that were there. So my interpretation of the theme, the depths below, is I wanted to do something that involved the planet, and I ended up going for something ground related. And the story behind that was I was at work one day and there was an earthquake and my coworker was just like, dude, did you feel that? And I was like, no. So like we looked everything up on USGS, and I kind of stumbled upon like a data set that they had with like every single earthquake or just like any sort of seismic activity that was recorded from 1965 to 2016. And I was like, hey, that's a data set, I can use that. So just a little background on why like depth was one of the most important factors I decided to use for like this model is that the depth of the earthquake can actually impact how strong it is and how much damage the earthquake can do. So I decided to use a linear regression model to try to predict the latitude of the earthquake using features like depth and magnitude. And the reason why I wanted to do a linear regression model as in comparison to like a neural network or something like that was the data that I got from the USGS, and I'll get into this like on the next slide. The data was very like, it was just all over the place. There were so many null values. There were like 23,000 or 230,000, I don't remember exactly, like earthquakes recorded. And there were like some data, like some like categories where there were only like 100 values. So I was like, great, that's wonderful. And so like, this is what I was talking about. So they had like 21 categories with like stuff that they recorded for like every single earthquake. And the ones that had kind of the most concise, or like just all of their information populated with latitude, longitude, depth, depth of the seismic station, so like the station that recorded the earthquake, magnitude and magnitude type. And so these kind of these 6 categories were the most important for just like being able to kind of figure out where the earthquake is. And the reason for that is there's this thing called the Ring of Fire, which is like kind of around the Pacific, just like the Pacific Ocean, and it's where there's a lot of like seismic activity happening. There's volcanoes, there's like subduction levels or tectonic plate subduction happening. There's all kinds of stuff going on, and that means a lot of seismic activity is concentrated in that region or in those regions. And so that's why like having magnitude type was important, in addition to like, all these other stuff. And some of these things, like date, time, horizontal distance and error, like a lot of these factors were actually just used to like record error that was recorded in like a different category. So like magnitude error, like there were 123 values for this. And it was just like, oh yeah, there might just be like, 0.5 plus or minus 0.5 for the magnitude recorded for this earthquake. So like a lot of this was just kind of like, stuff for logging reasons and just like describing stuff in other categories. So I kind of was like, okay, we don't need those. And most of the work that I did for this was actually on like cleaning up the data because I was using such like a simple classifier. Cleaning up the data was the most important thing for this. And so I cleaned up outliers using the Z-score, which is like a specific thing, and common sense. And so the star for common sense comes kind of from like how earthquakes happen. So most earthquakes most earthquakes have a recorded magnitude of about 5 or so, and most earthquakes occur at a depth of either around 10 meters below the Earth's surface or 30 meters below the Earth's surface. So the data that I got was very, very skewed. And so for the depth of the earthquake, they had like the range was from like -1.1 all the way to like 6,000, I think. And so that would have, skewed my model. When I like ran it, I got accuracies of like -900,000. So that was something I definitely needed to clean up. I also did one hot encoding for magnitude type. And the reason for that is like based on what kind of magnitude type is kind of describe what kind of earthquake happened. And I needed to balance the data in the depth category because, as I said, most earthquakes happen from like 10 to 30 meters below the Earth's surface. But most of them do happen like 10 meters below the surface. So that like there were 6,000 or 7,000 points recorded at 10 meters, and then there were like 2,000 recorded at 30, and there was like nothing in between. So I had to delete some of the entries in the depth category in order to like even out my model a little bit. And so this is some of the code for how I like did, some data processing. So like over here, this is where I kind of dropped everything that was like less than 0 and greater than 30 for depth. And the funny thing about this, so USGS records all seismic activity. So there were stuff like, oh, nuclear power plant explosion, or like there was another category that like was one data point for. So like everything that wasn't an earthquake didn't matter to me, so I just got rid of that. I got rid of all the null values, and I ended up with around, I'd say 8,000 or so data points after doing all the stuff and like one hot magnitude type, evening out the data. I ended up with around 8,000 data points. And so these are the results that I got. So I ran a linear regression model, and I got an training accuracy of 45, test accuracy of 51, which is like not too bad considering I was trying to predict nature. I also ran a second degree polynomial regression because anything higher than second degree would give me like -1 million accuracy. So training accuracy, I got 49%, test accuracy of 52 or 53, I guess, if you round. So it wasn't too terrible for trying to predict something that is unpredictable. Some of the issues that I ran into, low accuracy, and that was again because the data set was like it contained all the earthquakes like everywhere from like 1965 to 2016. There was a lot of missing information. Yeah, so you can kind of see here like 23,000 roughly like earthquakes or like entries were in the data set. Like for some of them, there's like 327 non-null values for some categories. Like a lot of it had to be scrapped. And some improvements. The first one I kind of thought to myself was find a new project. This is so stupid. Why are you trying to predict something that like it's such a stupid thing to try to predict? But like really, I would like to find a better data set. Ideally something location specific, which I think is, yeah. So it's like, a more updated data set with like, all like every single entry that I need like actually filled in, and maybe location specific, because a lot of earthquakes that happen like deep sea, like at like, below the ocean where there's like a subduction level happening, the depth for that would be a lot lower maybe, or like the magnitude type would be a lot different. And so we'd have different kind of, you know, geographical positioning. So maybe trying to be a little bit more like location specific would probably yield me better results. And also maybe using multiple data sets to kind of fill in the blanks almost. And the third one was to try building a more complex model. So for like all the intents and purposes of like this current project, I just wanted to see how like modifying data would yield different results. And so that's why most of the work I did was in, you know, changing the data. But maybe if I had a more complicated model, something that I could fine tune a little bit more with like different hyperparameters rather than just cleaning up the data, maybe I could get more accurate results. And that's it. Thank you.
You said you were predicting latitude?
Yeah.
So one of the things you had as your parameters was size, depth of the seismic station. So would that be the things measuring the seismic activity? Oh, would that create some form of bias? Because would it then not be predicting, oh, let's say all the stations that have a depth of 100 feet are all in this one latitude? Is that ever an issue or?
No, it was not. The depths of the seismic stations were actually like they were like all over the place kind of. Some were like 600 feet below the ground, others were like, you know, at the surface. And the latitudes that I looked at, I didn't look at all of them obviously, but I looked at a few of the latitudes and longitudes for the seismic stations, and there wasn't a lot of like repeated differences.
Any other questions? No? All right.
Okay, so